In this lecture, we will discuss about Truss analysis using flexibility matrix. And we know that Truss member carries only axial. There is no bending moment in any part of the Truss member. So, in any Truss member, either compression force or tensile force exist. The deflections due to the applied loads can be determined by Indeterminate method and other methods. So many methods are there, but one of the methods is Indeterminate method that we follow here, so that we can get the stiffness pattern. So in general, from Indeterminate method, deflection at ith coordinate, system coordinate, due to load, external load, is equal to summation of F small fi L by A, where capital F is the force due to the applied loads on primary structure, because in stiffness method, we usually, in the flexibility matrix method also, we actually apply the method only on primary structure. Okay. So in stiffness method, we apply everything on the spine structure. That is the primary structure in stiffness. Therefore, capital F is nothing but the force in each member or member force due to applied force. Okay. Small fi is the force developed in each member due to unit. Okay. So L and A is the number of geometry property of. Then the flexibility coefficients are calculated using the expression small delta ij is equal to summation of fi into fj into L divided by J. As small fi, or here the displacement coefficient small delta ij indicates the displacement at ith coordinate due to the unit load applied at jth coordinate. Okay. So is equal to summation of fi, that is the force in each member due to the applied or unit load at ith coordinate. Similarly, fj is the force due to unit load applied at jth. Once we have these displacements due to external loads at each system coordinate and the displacement coefficient, so therefore finally flexibility matrix, then we can apply compatibility equation to get the written dynamics. That is delta small delta into P, everything in matrix, delta small delta into P is equal to capital delta minus delta. Here the capital delta is nothing but the final displacement, okay, at this system coordinate. For example, say at system coordinate, if there is a final settlement, like that. If nothing is given, then delta is equal to 0. The next delta L is nothing but the deflection due to external load. That already we have now computed using the summation capital F small f I L double J, that expression. Okay. So once we have the redundant forces, then we can easily find out final number force. That can be calculated using the expression xi, number 4, ith number 4, final number 4 is equal to force due to external force in that F plus the summation of the force contribution from each redundant force, that is Fj into P. Okay, so Fj is the unit code contribution at jth coordinate and Pj is the actual force, redundant force acting at that j. So if you multiply, you will get a contribution of the force from the redundant force at that particular point. Now we will try to solve a problem so that we will get understood much better. So analyze the pin jointed plane frame shown in figure. The numbers in parentheses, actually not, the parentheses are missing actually. Okay, this is the cross section or cross sectional areas of the numbers in mm square. This is the cross section area 6,000 mm square for AB member, and for BC member again 6,000 mm square. Similarly, for BF this is 3,000 mm square area. Okay, so the pink color, not pink color, actually somewhat sandal color. Okay, or indicating the area of the particular numbers. Okay, so supports A and D or hinge and one 300 kN point load is acting at F joint and 600 kN is acting at E joint. Okay, this is 4.5 meter span each panel, then overall height is 6 meters. So in flexibility matrix method, the first thing is we have to identify the redundant. Okay, redundant force. For that, we need to calculate the static indeterminacy. Static indeterminacy internally and externally, both we have to calculate so that we can identify which is not extra, which is redundant in the structure, either member or reaction or force. So that we have to remove from the structure to make the structure primary in flexibility. And in stiffness method, actually irrestricted. Okay, that we will see in the next video. So primary structure, number of reactions is equal to R, 2 at support A and 2 at support A. The number of members we have M is equal to 10. 1, 2, 3, 4, 5, 7, 8, 9, 10. Okay, there is no joint here. Okay, there is no joint. It is a single number. FC is a single number. B is a single number. Okay, because there is no point is given. There is, for example, there is no notation is given in this junction. Therefore, that indicates that there is no joint star. So FC is a single number. P is another single. Okay. So suppose if the point is given specified by letter, then that indicates that each number, each portion is a separate. Okay. So in this case only FC and B, we have two crossed. So the number of joints is equal to 6 because 1, 2, 3, 4, 5, 6. Okay. Now we can apply the expression to find out static indeterminacy, that is degree of static indeterminacy. CS is equal to M plus capital R minus 2J, which is equal to, that means we have two redundant forces or members or forces. Then you have totally two. Okay, totally two. Therefore, in order to find out separately which are the redundant, so we calculate using the expression CSI is equal to M plus 3 minus 2J, which is equal to 1. That means we have static indeterminacy internally to simplicity. That means we have one extra term. Similarly, DSC external static indeterminacy is equal to capital R minus 3 it is equal to 1 decade. Therefore, that indicates we have extra reaction than the required. Therefore, redundants are any one reaction and any one. So, if you choose the appropriate reaction and member, the final structure should be stable. That's the only condition for the selection of the member or reaction. Okay. So, we consider horizontal force at D and member force Fc as our redundants. Okay, that means we will remove HD at support D and member Fc from the structure in order to make the structure determinate and stable also. That means we finally get a primary structure. So this is the primary structure where we remove HD, therefore this support becomes horizontal. Initially it was hinge support. Okay, once you remove the horizontal reaction, then the support becomes horizontal. That means we have only vertical reaction. And here we have removed Fc, member Fc. Therefore the force in member Fc will react now as the external redundant external force. So that is indicated by this color. So standard colors are our redundant. Okay. So actually this is the determinate structure, the black color determinate structure, which is our primary structure. Okay. Only primary structure, the flexibility matrix method should be employed. Okay, we can't apply so that no flexibility matrix method on indeterminate structure. So we have to make the structure determinate, which is called primary structure or least structure or base structure. On that we will apply flexibility matrix. Okay. So next step is to assign some number to the system called system coordinate. 1, 2, and here we have only 2 redundants, therefore we will have only 2 system coordinates. Number 1 and number 2. So here we assign number 4 direction as system coordinate 1 and horizontal HD direction as system coordinate. Okay. So whenever in matrix the first element, first row 1, okay, stands for the number force. The second number 2, system coordinate 2, represents the horizontal direction. Okay. So once we have the system coordinate and the primary structure, then we can go for the actual moment calculation. Here in Truss problem there is no moment but force calculation. Beam and potential for moment calculation, but here for Truss problem we find out the force of each one. So to find out members, Truss member force, usually we have so many methods. Out of those methods, this method of joint, and actually we are going to use. Okay, a very simple method. So we are going to use joint. The force calculation and the tension is taken as positive tension force in numbers and compression number as. So this is the sign convention we are going to follow. So this is the table we are going to use. First one is member. Here I have listed all members starting from AB, AF, then BC, BE, BF, GF, CF. Totally 10 members. Okay. And L by A, because in our displacement coefficient expression as well as displacement expression, we have L by A, E. That's no ratio. That's why because E is common to all numbers. So we take out E, and here we compute L by A ratio. But L by ratio is different, therefore we compute L by A first column. The next column is capital F. Capital F is nothing but the force, member force, or the force in each member due to external load alone on primary structure. Remember, on primary structure. So on primary structure, we will put all the external loads as given in the problem. Then we will sort out. We will find out the member forces using method of choice. That we will list out with capital. Then small f1 column, we remove all the external loads. Okay. Now we will have only primary structure. On the primary structure, we will apply unit force, unit load along system force. Now we will find out the force in each member. Okay, using method of joints, and we list in this column. We list out in this F1. F2, we remove all the loads. Now we have only primary structure. On the primary structure, we will apply unit load at system force. Now we will find force in each member using method of joints again. Then we will list all those forces here. Okay, so only these things are just using method of joints. This one, capital F, small f1, small f. Only these three columns we have to apply method of joints. All others are just substitution, because for all others values are already produced. Therefore, we can compute this. Okay, L by A given the problem, therefore we can compute F, F1, small f2. We have to use method of joints to compute. So once we know these things, the four columns, then you can substitute the values here. Capital F F1 divided by A, capital F F2 divided by A. This is nothing but delta 1L. This is nothing but delta 2L. Okay, this is nothing but small delta 1. Here V1. Here this one delta 1 2, delta 2. So in this problem we have only two degrees of freedom. Okay, two redundant actually, two redundant. Therefore the size of flexibility matrix will be 2 by 2. And flexibility matrix are symmetric. Therefore we have to find out only half of the upper half of this. Okay. So we have to find out delta 1 1, small delta 1 1, small delta 1 2, and small delta 1. Because small delta 2 1 is nothing but delta 1. Okay. Now we list out, write down all the values of L by. So for example, say for AB member, this L by A is 1.25 by A is 1.25. The L, if L is not directly given, then we have to use the factors theorem or trigonometry, whatever, to find out the length of that particular. Okay, so that we get 1 point. So either we can put in meter unit or mm. Okay. So to fill up this column, the next column, we have to use method of. So before going to apply method of joint, okay, each joint, first we have to find out the reaction, because the primary structure is a determinate structure. So you can apply equations to get the reaction. So which will be used in the method of joint. Therefore first we have to find out RA and RD using sigma M is equal to 0 and sigma B is equal to 0. So checking moments about D, RA into this distance, okay, 4.5 plus 4.5 plus 4.5, and minus 300 into this 9 meter, minus 600 into this 4.5. Okay, Therefore, RA is equal to 400 kilonewton, and applying sigma V is equal to 0, we will get RD is equal to 500. So now we have the reaction for RA and RD value. Therefore, we can start a method of joints. So in method of joints, first we have to choose a joint in which we have less than or maximum of 2 unknowns. Because at each joint we have only 2 equilibrium conditions, sigma h is equal to 0 and sigma v is equal to 0. Therefore, only 2 unknowns can be solved. Therefore, we have to choose first the joint such a way that in that joint the maximum of 2 unknowns are available. Okay. Therefore, we choose first joint A. So this is the joint A. At joint A we have reaction RA acting upward, and at joint A we have 2 members. Okay, leaving from that point A. So here is the AF member. So when you cut a member, the internal force will emerge out. That is the force F AF. Similarly, if you cut that member, the internal force will emerge. Therefore, that force is more specified as capital F AB. So this is the AB member, this is the AC. This is the theta. Okay. Now initially we assume all forces in the member are tension. Tension means pulling away the point. Junction means joint. Okay. Pulling away the joint is actually tension. Is clear? Okay. Initially we don't know because the type of force in the member is not known initially. Therefore, we assume always all positive things, because tension force is considered positive. That's why we assume initially all member force are positive. That is tension. Clear? Later on, if you get negative answer, then that indicates that member force is actually compressive, not tension. Okay. So this is the scenario. Now we can apply sigma v, because at each joint we have only 2 equilibrium equations. One is sigma v is equal to 0, another one is sigma h is equal to 0. So which expression, which equilibrium equation we should use first? Okay. Which equilibrium equation gives you directly the unknown value or the value for unknown. For example, say here, this is the vertical force, this is the vertical reaction, which is a known value. Okay. This is the horizontal force, unknown value. This is the inclined force, unknown value. But inclined force will have horizontal and the vertical components. Okay. Therefore, here already we know vertical force reaction. Therefore, if you use first sigma E is equal to 0, then you will get directly the vertical component, or indirectly the inclined force FAB. So once you know FAB, you can calculate this FAF using sigma h is equal to 0. Because if you in sigma h is equal to 0, this RA won't come. Only this FAF and the horizontal component of FAB. Okay. Therefore, in this first we apply sigma v is equal to 0. In sigma v is equal to 0, only vertical forces are involved. Vertical force in this joint are RA and the vertical component of this FA. How to calculate vertical component? See, make a triangle in which the hypotenuse is the member force. So this is a triangle. See, this is a triangle. Okay. So here we have 90 degrees. So we want the vertical. Vertical means just opposite to theta. That means sin theta. So FAB into sin theta will give you the vertical component of this force. That we have to write. But next thing we have to decide whether it is negative or positive. For that, just revolve this one, just and like this. But still RO is upward. Still RO is upward. Here this RO is also upward. So we have to, in sigma V is equal to 0, we have to group all upward forces equal to all downward forces. But here RA is already upward force. The vertical component of FAB is also vertical. So group them together and equal to 0 because there is no downward force. So from this expression we can get FAB value because RA known, sin theta. Sin theta you can get from the here. So from the geometry, AB is equal to 7.5 meter length and AF is given 4.5 meter. Then PF is given 6 overall height of the truss. So therefore theta, sin theta is equal to opposite side divided by hypotenuse, that will be 6 by 7.5. Cos theta is equal to adjacent side divided by hypotenuse. So 4.5 by 7. So therefore FAB is equal to minus RA divided by sin theta, which is equal to minus 500 km. So minus indicates that FAB initially assumed as no tension is actually a compression. Okay. So whenever you have, so keep this symbol as it is for the entire problem, not getting confused. Okay. But wherever we have FAB, that time you have to substitute minus 5. Okay, that's enough. Therefore, next we have to compute the FAF. FAF is in horizontal direction, therefore we have to apply sigma is equal to 0 to get this value. Therefore, FAF is equal to 300. So it is so positive one, therefore our approach is that value we have to go opposite. Against AB minus 500 plus and against AF plus 3. Okay. Now next we have to go for the next area. So we consider next F joint. So here we have 3 members, but out of 3 members already we have calculated the member force for AF. That means FAF actually. So the remaining unknowns are, one is force in FE, another one is force in okay. Still, okay. So here also we assume initially all are positive, all are away from the joint. We initially assume all positive. Okay. And one 300 kilonewton external load is also acting at. Okay. So it is there is no inclined force, therefore you can directly get the force by simply applying sigma equal to 0. Sigma is equal to 0, you can get that. Okay. Therefore, either equilibrium equations you can use first, because in each direction we have one. Vertical direction we have 300 kilonewton, horizontal direction F. From sigma V is equal to 0, we get F dF is equal to 300 kilonewton tension, and sigma V is equal to 0, we get F F is equal to F AF. Again, F is also 300. So both are equal. Now consider joint T. So this is a joint T where we have 2 members, a DE as well as DC, and one vertical junction R. So one is inclined member, another one is horizontal. But the known value is in vertical direction, therefore first we have to use sigma V is equal, so that we directly the value of F. So therefore FTC with sin theta is the vertical component of FTC force plus RD, because we assume everything in the opposite direction of the tension. Therefore both are the same, plus is equal to G. Therefore FTC is equal to minus RD sin theta, which is equal to minus 625. That is compression. Okay. So DC is actually compression, not tension. So wherever we have FTC, we have to substitute minus 6. But still we are using this one. We never change the arrow here. We still use, then for entire problem use this type of arrow, that is tension arrow, but we substituting the value just use minus 6. Okay, so that will not confuse you until you get the exact answer. Now apply sigma is equal to 0 so that you will get FTE value. So FT is equal to 375 kilonewton, that is tension. Now we will choose joint C. So this is the joint C where we have 3 members. Out of 3 members, 1 member force is already known, FTC. Only FPC and FC are not. Okay. Therefore, see here the inclined force is known value. The vertical and horizontal force are unknown values. Therefore, here also any equilibrium equations can be used first, because sigma E is equal to 0 means you have to use the vertical component of the inclined force, which is unknown, which is known, and the FC. Similarly for horizontal, the horizontal component of FTC which is known, and FBC which is unknown. Okay, so in either way you can, or always use sigma V equal to 0. So by applying sigma V equal to 0, FTE, okay, FTE is acting downward, FTC sin theta. This vertical component of FTC also acting downward. Therefore we are grouping on one side. Is equal to 0. Is equal to other side means all the forces acting upward. But in this case there is no upward force. Therefore this is equal to 0. Therefore FC is equal to 500 kilonewton, which is tension. Similarly, applying sigma is equal to 0, we get FBC is equal to minus 375 kilonewton. That means compression. Next we will see the joint E. So in joint G actually we have 4 members, but 3 members of the forces of 3 members already known, computed. So only one is left. Therefore you can use any one of the equilibrium equations, either sigma V equal to 0 or sigma H equal to 0 to get, because FB is an inclined force. Therefore you can use either equilibrium equations to get the value of FB. Here I use sigma V equal to 0. So all vertical forces we have to group it, and FCE vertical force upward, and the vertical component of FB is also upward. So group on the one side, and system kilonewton is acting downward. Therefore that other side. Therefore FB is equal to 125 kilonewton tension. So we have calculated all the member forces due to external loads. Therefore that we have to list out on the table under capital. So this is the member forces. The CF nothing, because we have removed that member. Therefore nothing is developed due to external load. That's a dash. Now we have to use the primary structure and apply unit load at the system component 1 and find out the member forces. So here we are applying unit load along system component 1, which is member FC. Okay. Here also we assume tension, positive. Okay. So due to this opposite load, there won't be any reaction. Here 0, there also 0. So RA is equal to 0 and RD is equal to 0. Okay. So next, based upon the zero member concept, we can put 0 before starting the set of joints. So here 0, here 0 because not just meeting at inclined things. Here also 0, 0. Okay. So the remaining forces can be calculated using method of joints. Now we now take joint F so that we will compute the number forces in Ft and Fb. Okay. Again, applying sigma V is equal to 0 and sigma H is equal to 0, we can find out. So Fbf is equal to minus 0.80 compression and FFP is equal to minus 0.6 kilonewton compression. So next, consider joint C. So here we have only one unknown number, unknown force, okay, which is FCE. Therefore, use sigma V is equal to 0. Therefore, Fc is equal to minus 0.80 kilonewton. Sorry, actually both are unknown. Again, from sigma is equal to 0, FBC is equal to 0.6 minus 0.6 kilonewton. Now consider joint B. So applying sigma V is equal to 0. So these values we have to list out in the table under small one. Now apply unit load at the system coordinate 2. Again, due to the application of unit load at T, here we have horizontal reaction just opposite HEA. Therefore, if you take moments, you will get RA is equal to 0 and RD is equal to 0 because just opposite force get cancelled each other. Therefore, both reactions are. So here also we can apply the zero number force concept. Okay, here nothing 0 0. Okay, so this is 0 means this is 0, this is 0. So only AF, this is the bottom chord, is remaining. All others are 0, and from sigma is equal to 0 at each joint we can get the values of FA, FG, FD, and all are actually tension equal. Okay, so this also we have to substitute in the table and we can compute other things. So once we have all the data, we can compute the other parameters. So once we have all these things, then we can come up with summation of F1 AA, similarly other summation. So this is actually the summation value. This summation value we have to substitute in the displacement expression. Therefore, deflection due to loads at coordinate 1, system coordinate 1 is equal to delta IL is equal to summation of capital F, small f1, L divided by AE. Already we have in the table, then directly write down that value. minus 1068.5 divided by E. Okay. Similarly, delta 2L. So delta 2L is nothing but 1462.5 divided by E. So now we can formulate the flexibility matrix using direct method. So this is the general expression for flexibility coefficient. Delta Ij is equal to summation of Fi Fj L divided by Ae. Already we have calculated F1 L divided by Ae, F1 F2 L divided by Ae, then F2 L divided by Ae. Okay. So just to know, copy from the table to formulate the flexibility coefficient matrix or flexibility matrix. So delta 11 is equal to 8.37 divided by E. Delta 12 is equal to delta 21 is equal to minus 0.9 divided by E. And delta 22 is equal to 4.5 divided by E. Therefore, delta flexibility matrix delta is equal to 8.37 divided by E minus 0.9 E, again minus 0.9 E and 4.5. Next we have to apply the compatibility equation. Delta into P is equal to capital delta minus capital delta L. Therefore, P is equal to inverse of small delta into capital delta minus delta L. The P redundant forces are nothing but member force in CF, that is FCF, and reaction at D, support D, horizontal reaction to support D, that is HD. So which is equal to the inverse of delta, that is the flexibility matrix. So here this delta final settlement at that is no member, but there is no final settlement or final displacement. Therefore it is 0, and DL is the displacement at that place or system coordinate 1 due to external load, that is equal to minus 1068.5 by E. Already we have minus here, so minus plus. And again the second along HD horizontal direction at D we have 0 settlement, therefore 0 minus this is the displacement at along HD due to external load. Therefore FCF is equal to 94.75 kilonewton, HD is equal to minus 306.05 kilonewton. So minus indicates that HD is acting actually towards left direction, okay, not right direction or left. Once we have the redundant forces, then we can calculate the member forces. So using this expression, member force, final member force is equal to member force due to external load plus contribution force contribution from each redundant force. That is Fi plus F1 P1 F2 P2. That means P1 is equal to FCF is equal to 94.75 kilonewton, P2 is equal to HD is equal to minus 306.01. So member AB force is equal to the capital Fi nothing but minus 500, and F1 is 0, F2 also 0 for that member. Therefore, the final member force in AB is minus 500 kilo. Similarly, we can find out the member forces for. So this is the end of